Welcome to part 2 of our IB Physics revision series on integrated concepts in mechanics and electricity, where we'll be focusing on paper 2 questions. Okay, so on the next slide, we will introduce our first paper 2 past paper question. Okay, so here's our first question, and it comes from the May 2016 HL paper 2 from time zone 0. And the question is worth 15 points, and it reads, a company designs a spring system for loading ice blocks onto a truck. The ice block is placed in a holder H in front of the spring, and an electric motor compresses the spring by pushing H to the left. When the spring is released, the ice block is accelerated towards a ramp ABC. When the spring is fully decompressed, the ice block loses contact with the spring at A. The mass of the ice block is 55 kilograms, and they also say that we assume that the surface of the ramp is frictionless and that the masses of the spring and the holder are negligible compared to the mass of the ice block. So there's quite a bit to process there, and we will go through that step by step in the next slide. Okay, so as we begin to tackle the question, you will find out that there is these two main topics that are relevant to this specific question. That's why we said that the integrated topics that we'll be focusing on are mechanics and electricity. And as far as this question goes, the topics highlighted or the subtopics highlighted in blue are the ones that are pertinent to this question. So we will be looking at all those in mechanics. So those 4 subtopics in mechanics will be relevant to this question, and that one subtopic, the heating effect of electrical currents. 5.4 is kind of implied, but you don't go into detail. We don't go into details of that in this question. So if you're curious about that, they're saying that you have a motor that is compressing this block. So of course that does include the magnetic effect of an electric current, because we know that if you have a current moving through a wire in a magnetic field, then it causes a force which rotates. So this is in the case where you have an a motor that is run by an electrical system, in principle uses that magnetic effect of electric currents, but we won't be going through that in this question specifically. Okay. So accounting for all the information that we were given, here is the first question, okay, which is question 1A, and it has 2 parts. Okay, so A1 says that the block arrives at C with a speed of 0.9 meters per second. So show that the elastic energy stored in the spring is 670 joules. So that's worth 2 points. And then the second part of the question asks, calculate the speed of the block at A. Okay, so before we answer the question, let's revert back to our syllabus and specifically the objectives that are tackled in this question. So we know that, the first objective in general is understanding concepts, and specifically in this question, the kinetic energy, gravitational potential energy, elastic potential energy, and work done are all relevant to answering this question. And then the applications is how to apply the conservation of energy using this idea of energy transformation. So transferring one form of energy to another. Okay, and as you will see, we are specifically transferring elastic potential energy in our spring that is controlled by the motor, and uh, that energy is transferred to gravitational potential energy and kinetic energy. Okay, so let's define potential energy. Okay, so potential energy is the energy an object has due to its position. Okay, and in the IB mechanics unit, okay, we are introduced to both gravitational potential energy and elastic potential energy. Okay, so gravitational potential energy is the amount of energy stored in an object due to its position in the gravitational field, while spring potential energy is the energy stored by a spring when it is either stretched or compressed by a distance x. So we will look at visual illustrations of this so that this becomes a little more clear. Okay, so let's define gravitational potential energy first. Okay, so if you lift a mass a certain height above the ground or above the earth, you have increased its potential in the gravitational field. Okay, so we say this because the force of gravity that we experience normally from day to day in our lives, okay, we are aware of it. We may not be able to see it, but it is there. And it is considered a force field. Perhaps it is a force, it exists, and it is exerting that force within a certain area, okay, specifically on the earth. And the force, the source of the force, I guess, or it appears to come from the center of the earth. All objects are drawn towards the center of the earth. This is why whenever you are a certain height above the earth, right, we know that the earth is spherical. So if you think of it perhaps like, when we launch satellites into the air, and let's say for one reason or another, they don't remain in orbit, then they will accelerate at a certain speed towards the Earth, right? It'll crash land on the Earth because it is attracted by the Earth's gravitational field. So of course, the magnitude of the impact, right, and the resulting energy that comes out of that impact is attributed to the potential that it had, the potential energy due to its height above the Earth. So the further above the Earth or the surface of the Earth that you are, the greater the potential energy that an object will have. So the height h is key, and therefore we can define the gravitational potential energy as the product of the mass, the force, the gravitational acceleration, and the height above the Earth. Okay. And here specifically, we are saying delta PEG just to emphasize that it is the change in the gravitational potential energy. So you may not necessarily be using ground zero as your reference point, but let's say you could be, comparing the difference between a height that is 5 meters above the Earth and another height that's 50 meters above the Earth. So what's the change in gravitational potential energy between those 2 points if you drop a rock between those 2 points, okay? And then, of course, just for a fun illustration, you can see that caveman over there. This is a crude, perhaps, way of breaking up a stone, perhaps for whatever reason that he was going to need it for to break it up. So you just put a much larger stone at a higher potential above the earth, and then, of course, it will accelerate due to the force of gravity. Okay, so that's our G value, and then its height h, the higher it is above the earth, will generate more force as it falls, and of course its mass, the more massive it is, the greater energy it will release, and in that case, consequently, it'll be able to break up whatever stone that we needed to break up, so the caveman needed to break up. Okay. Okay, what about the spring potential energy? Okay, so here we have an illustration, okay, and part A shows the spring at rest, so at its equilibrium position. And as you can see on the diagram, that dotted line in purple with the label x is equals to 0, that's your equilibrium position. So the spring is at rest at that point. And then the next diagram, a horizontal force F, labeled more specifically as Fp, in the diagram in green with that green arrow, is applied to stretch the spring a distance x. So on the diagram itself, Fp means the force, the pulling force that is applied. Okay, and as you can see, x is the displacement from equilibrium. Okay, so if the spring is released, so that pulling force is no longer in effect, right? So the person who was pulling it stops pulling it. Then the Fs force, force in blue, okay, which is equal and opposite to the pulling force that was initially applied. So Fs is this counteracting or the restoring spring force, pulls back the spring to its equilibrium position. So the spring's elastic property pulls the spring back to its equilibrium position. And as a result, it transfers the potential that it had, that elastic potential that it had, and it transfers it to kinetic energy. So the act of pulling it means that you increased its potential energy, just like in the gravitational field, right? When you put something a height above the ground, you are giving it potential energy. So for the spring's case, it's a similar principle. So you're pulling it away from its equilibrium or rest position, and you're giving it potential energy. And then once you release that force, then the restoring force from the spring, or which is elastic in nature, um, it transfers that energy to kinetic energy, okay, as the spring is moving back towards its equilibrium position, okay. And if you look at the last diagram now, part C, this also applies to a compressing force as well. So a spring can either be stretched or compressed. So in the diagram, you can see now we are applying a compressing force Fp, which is now the blue part. Okay, so you are compressing it away from equilibrium. So if you look back at that dotted line at x is equals to 0, so it's approximately the same distance x as the initial distance that you stretched it out to, right? So you're compressing it at distance x, and then when you stop applying that compressing force, then our restoring spring force Fs, now in green down there, restores the spring back to its equilibrium position. Okay, so spring's potential energy can therefore be expressed as half kx squared. So this is the formula for the spring's potential energy. Okay, where k is the spring constant of the spring. Okay, that will make sense. That makes sense because obviously how springy or how elastic the spring is dependent on the materials that were used to make the spring. Okay, so if you go back to your physics notes and study Hooke's law, then you know that will become apparent. Okay, and then x is the deformation. Okay, so if you're wondering how this formula came about, um, essentially the spring's potential energy is the work done by the spring force. And in the topic of work, we know that work is force times distance. Okay, but whenever you're stretching a spring, you start with a force of 0 and you reach a maximum force that here we're calling Fs. So if you look at that, illustration there, those equations there at the top, we're saying that the average spring force that is applied to a spring is given by your initial force, which is usually 0 before, as you're just starting to stretch the spring, until you reach the maximum value of the force, till your stretching point, whatever it is that you've decided is your maximum stretching force. So it may or may not be at the object's elastic or at the spring's elastic limit or not. So it just depends on how far you decide to stretch it. Okay, so what we're saying is that we can summarize that the force of the spring is generally the average of that, between that 0 value and that maximum value. So that's why we're calling it Fs over 2 over there, okay, on the top right hand corner. So if we apply that work done formula, that force is the force times the distance. So our force is Fs over 2, our average value, right? And then you multiply that by the distance of stretching, which is our x, right? So we are stretching it far from, away from equilibrium, the distance x, okay? And then we substitute that spring force Fs with the formula from Hooke's law. So again, if you go back to Hooke's law says that, the force is proportional to the extension, which is your x, and then the constant in that case is just your k value, which is dependent on the spring's properties, the material properties. So therefore, if we replace that Fs, or a spring force, average spring force value, by kx, and you multiply that by the distance that it stretches, x, then you get kx squared. So therefore, our work done by a spring, which is essentially our elastic potential energy, is kx squared over 2, or a half kx squared. Now, the last concept we need to understand in order to solve our problem is the conservation of mechanical energy. So we have already defined what potential energy is, and specifically the two kinds of potential energy that are in our question: gravitational potential energy and spring potential energy. Okay, and we have seen that those get converted to kinetic energy once that potential energy is released. So when we're talking about a rock that is, above the ground and it is released, so that rock's potential energy at a certain height above the ground gets transferred to kinetic energy as it's falling. And then for the spring's potential energy, we have seen whether you stretch or compress the spring. Once you release that force, then the restoring force of this spring accelerates it back to equilibrium position, right? So it gives it kinetic energy. Okay, so now that we've established that, okay, so for any frictionless system, the mechanical energy is always conserved. So mechanical energy consists of only potential and kinetic energy. Okay, so this question is telling us to assume that we are working with a frictionless system, which is an idealized case. Of course, in real life, most interactions do not tend to be just purely consisting of potential and kinetic energy. There is always some loss of mechanical energy due to friction, heat, sound, etc., etc. Okay, but here they've asked us to assume that the system is frictionless. So in that case, what that means that there is only a transfer between potential and kinetic energy, and when that happens, the total mechanical energy of the system remains constant. Okay, so here you can see that expressed in equation form. So delta Ke plus delta Pe is equals to 0. So that means our change in our kinetic energy plus our change in potential energy is always a constant value. Okay, so if we rearrange that equation and then move the change in potential energy to the other side of the equation, it means that a loss in potential energy um, is usually equivalent to a gain in kinetic energy. Okay, so if you look at that diagram there, okay, or that picture, okay, so this was taken from the phetcolorado.edu site, okay, which is a great site if you want to, try some simulations on various types of physics concepts and in other subjects as well, other pure science subjects, biology and chemistry, etc. Okay, but this is taken from their energy skate park simulation. So this is a snapshot of a skater who's on a ramp, okay? So they originally start off at a very high height, and the setting is that this system is frictionless. So in that case, the skater's energy, total energy, just consists of uh, kinetic and potential energy, okay? So it's just a purely mechanical energy system, okay? So at the point where the skater is, as you can see on the diagram, they have kinetic energy, a smaller value of kinetic energy than their potential energy, but they're almost approximately the same. So what that tells us is that at that point where the skater is, they have they're gaining kinetic energy as they're moving from their highest point on the ramp. So at the highest point on the ramp, that green bar would have been negligible. You would not have been able to see it. Then the blue bar would be the same height as the total energy bar. Okay, the brass or coloring that you have there. Okay, so those would be the same height when the skater is at the top of the ramp. So that tells you that the total energy of the system is constant. So when the skater is at the top of the ramp, all the total energy is equal to the potential energy, the maximum potential energy. But then as they skate down the ramp, then that total energy gets divided up between kinetic and potential energy. So if you did sum up what the value of that green bar was and you added it to the blue bar, you would get the brass colored bar. Okay, so at the point where the skater is, they have both kinetic and potential energy. So their potential energy is still significant because they're a certain height above the ground, but their kinetic energy is increasing slowly. So at the bottom of the ramp, where you have that U shape or the bottom of the bowl, the total energy will be equal to the maximum kinetic energy. So in that case, they will have no potential energy at all because they are at ground zero or their height is zero, but they will have the maximum speed at that point. So their kinetic energy, the green bar, will be the same height as that total energy bar.